Hello everyone, welcome back. In today's lecture, we are going to use the PySPH framework to write and solve this particular shock tube problem. Let me create a new file, name as SPH shock.py, and also make sure here that I am using the PySPH environment. Then I'll use these two tabs so that I can track that what I was using here. I'll use the same things in here as well. First of all, I'll create these particles. In order to do so, first thing I have to import an application, PySPH.solver. From PySPH import application. You can create a subclass of this particular class shock tube application, then define init. Usually this particular init should not be used. You can use initialize, which is a method which is passed with this application class. You can initialize whatever you want here. Right now we are not going to do any initialization. We are going to use these global values. Then you can do this create particles. There are various methods here and some of them are mandatory. If you don't overload some of these methods, then this application won't run. Create particles. Here this should return an array. So you can check here in the definition that it creates the particle array and returns a list of them. So it returns a list of particle arrays. So let's also import one of the method which you can use to create particle arrays. In the base, in utils, you will find get particle array. We are going to use that. Before that, we have to generate the coordinates and the corresponding pressure values, energy values, and the rho values. Let's do that. We are going to use this particular loop as it is. I'll create here x values is equal to this empty array, and then let's name this x's are this x's dot append x, and similarly here I want x's dot append x here. So in this way I'll get all the x values, and let's see how we have initialized this. We have initialized like this. We'll use the same pattern. P's is equal to this. Then what else? Here we have rho, p and u. Rows as, let's name them as rows, rho and p only, and the last thing was u. So u is 0, so we need not to do anything for that. P dot append, this is 1.0 and rho is also 1.0. Similarly we have to do here. So this should be 0.25 and this should be 0.1795. right? Now we also need the h value. The h value is 1.2 times the dx, which is here dx, and we also need the mass. Mass is already defined here, so we need not to define again. Then you can create the particles as get the particle array, the name of this particle. You can write like this. The name is say air. You can have any name, and then you can write whatever properties you want to add. X is equal to x, whatever is here by default and you don't define it, then it will be initialized as 0. And you can also define something like this. I am passing this as an integer or a float, not as a list, but since this is a list, it will create a list which will have all the element as 0 in that particular list or array. Then I also have pressure, P is equal to P. Similarly I have rho, which is equal to rho, and I need to compute energy. I'll use this particular formula here, which is equal to P divided by gamma, which is defined here, minus 1 times rho. E is equal to E, and u, we have not defined u yet, so let me move this the next line. U is equal to u, and there is no v and w. U we are initializing as 0 as initialized here, and then we can have du is the acceleration. For this we can write au as 0. Similarly, a rho is the acceleration of the continuity equation. Although we are not going to use the continuity equation, we can set this, we can choose to not have it. And acceleration in the energy is this. D rho we are not going to use at all. Here it is defined, but and it was initialized, but here in the integrator it was not used. Now we can return this as an array as particles. Now the next thing is to create a solver for this. Before that, we have to create these equations. So equations must be passed as a subclass of equations, and similarly this stepper should be passed as a subclass of an integrator. We have to do that as well. Let's first do that. From PySPH dot SPH dot equations import equations. There are various pre-written equations that are present in PySPH. You should explore that, and also there is a read-the-docs where everything here that I am explaining is explained in a well documented manner. You can also look at that documentation, and then in SPH you can also find the integrator. Here I am going to use Euler integrator, and you can also have the integrator step as the integrator step. This I'll subclass this and use this Euler integrator as it is. So you can look at this Euler integrator. What is this? So it takes one time step. It first computes this acceleration, which is this part, and then in the stage 1 it does whatever is done in the integrator step in the stage 1 method. It will do that, and then it will update the domain. In the update domain it will perform any kind of copying for periodic boundary condition or various other things like updating the nearest neighbor. And you can have a method in the post stage. You want to update something after this stage update, then you can do that in the post stage. We are not going to touch that. We'll just use the Euler integrator as it is. Then I'll have one class for this equation. Let's call this as momentum equation. Momentum equation is equation. First you have to write the initialization. You have to initialize the acceleration. Whatever is computed in the previous time step, you don't want it to be there. You want to add this particular acceleration on the I particles due to all the j particles which are the neighbors. So d underscore tells you that it is taking the destination array. In that I want this particular property au, and the index is d underscore idx is the index. For this is the syntax of PySPH framework. You have to use this only. Then you can say that d underscore au d underscore idx is equal to 0. You initialize it. Whatever is done here is done by this particular method, and you don't have to write this particular loop because this is done by the PySPH framework. Then you have to use loop. In the loop it takes all the neighboring particles, whatever operation you want to do, and it takes those neighboring particles and do this particular operation that you write inside this. Let me show you how to write it. You take all the destination index, all the index of the neighbors, and for the momentum equation you want the mass which is globally defined. You can use that, or you can pass it here in the init. You can say that you need the mass. Actually the mass we have already copied here. Oh, we haven't. That's why we have to create m equal to m and h equal to h as well. These two are also required, so we need not to pass the mass then in that case. Here you need the mass and then del p. That means the del p is coming from the pressure of the ith particle and pressure of the jth particle. Therefore you need the pressure from the destination and source. So anything that is coming from the source should start with s underscore and the property name. except that we need this, which is the kernel gradient. Kernel gradient is passed as dwij. This computes everything which is inside this kernel gradient. It takes the distance between two particles and takes the dx value and computes that. Given this, you can write del p is equal to d underscore p. So I am writing this one now, which is here, the pi, which is d underscore p d underscore idx, and this divided by rho. I have to pass rho as well, d rho and s rho. So d underscore rho, d underscore idx, this whole squared, and then plus this whole thing for the jth particle, which is in s. So sp s underscore idx divided by s underscore rho s underscore idx whole squared. This is my del p. Now I have to add this here. This is my du, which is negative m times del p times this. My dau d underscore idx is plus equal to, I have to use here d underscore au as well, is negative of d underscore m didx times this del p times dwij, and here I have to say that this will give me all the components of the gradient. I need just in the x direction. Here this was not required because we were already doing it in one dimension only. And this kernel definition we don't need because this PySPH already have various kernels. You can just import it. So I'll import the kernel from PySPH dot SPH dot kernels import. This one was the Gaussian kernel, this. So I can just type Gaussian and I'll get the Gaussian kernel. Now the next thing is we also need this particular equation, which is for dE. I'll copy everything from here because everything which is here is similar to that. Now we have to compute this del p twice because this is not common. Now these are two different equations, but this is much faster because this particular del p you can also keep as a property and compute these ones, but this is not recommended because this requires the neighboring information as well. I'll write this as energy equation and energy equation, and then here we need the acceleration due to the energy is ae. I have to change this to e, and here also the energy, and with this I also need the velocity du and su. I need the del p as it is, but I also need du, which is equal to, so del v is ui minus uj. I can just type du d underscore idx minus d underscore s underscore u s underscore idx. This is du, and my d underscore ae is equal to this negative 0.5 times the mass, which is this, times del p times this du times this dwij. And with this we also need this, which is computing the density. This is also can be done using this, which is summation density. This is also an equation, and here also I'll initialize rho and idx and then define the loop. Here I just need the mass and the kernel. Kernel is, this is the mass, and just the mass of the destination. D underscore rho didx is equal to m didx times wij. This is the kernel, not the gradient, no component here. These are the three equations that you will need, and remember that these need to be solved in certain manners. First, for all the particles we need to compute the density, then for all the particles we need to compute the acceleration. For that we have to define something like this. You have to write create equations. You can see here it should also return an array of all the equations, but along with that we also need them to be have in certain groups such that it knows that what to solve first and then what to solve. For that we also require something called group. So we can import this from here only. With the equation you can also have group. Now you can write something like this: summation density equation is equal to summation density. What are the destinations? So destination is all the air particles. You have to write like this, and then sources can be multiple, therefore this should be an array, all the air particles. Then you have the momentum equation, which is momentum equation same as this: destination is equal to air and sources is equal to also air. Similarly, the energy equation, destination is air and sources are also air. Now here you can define something like this: there is one group, this group 1, where the equations that need to be solved is just the summation density. And after this, do you want to update the neighboring information or not? Since we are going to use a periodic boundary condition along the ends, because in order to apply a zero gradient boundary condition, it is relatively difficult. We are going to use the periodic boundary condition. Let me just see what was used here. I think here nothing was used. It was as it is because there was no change, the gradients were 0. We can also do that. We are not going to update anything here. Summation density we are going to use as it is, and after that no other argument we are going to pass, but you can set that whether this is going to perform certain iterations. Let's say these set of equations, you want them to run 10 times before moving to the next group. This is one group and this should be an array. Then the next group, which is again equations, and here you want these two equations to be solved: momentum equation and the energy equation. And the order of these equations does not matter, because even if you write this before and this momentum equation after, it will solve both of them simultaneously. Here the order does not matter, but here the order matters. First it will run all the equations here, then it will run everything here. Now we can pass this. Let me write this as equations equal to this, or let me write all equations and return this. Now the next thing, once you compute these two, you need to integrate. In order to integrate, we should have an integrator step. So let's create an integrator step, Euler integrator step, which is a subclass of integrator step. Remember that in the integrator here, it requires you to have a stage in the integrator step. The stage 1 calls the stage 1 in this integrator. Let me also show you one of the integrator in this integrator step. You can see here the Euler step is something like this. Let's copy this one only. Here we have stage 1, which looks something like this. No need to initialize, because we also have an initialize method here, which is initializing all the accelerations. Here for this, the velocity is getting updated from the acceleration, and then this is multiplied to the dt. This is what we are doing here. The du is updated, basically this point, and then this goes to this position. This is same as this here, and then du is getting whatever is in au. We don't need these two, we also don't need these two. And here for the density we don't have anything. For the energy, we have to update the energy, which is this dt times the acceleration dae d underscore idx. Let me write here also all those. So this is dae, and we don't need xyz, just the x. So here, unlike these equations, we have access to dt, which does not have a d underscore or s underscore. Also we have access to time here as well. We don't have x and we don't have e. Let me add them. Now this much is done, and here we also have a equation of state, which we are doing updating somewhere here, this. So we can have a separate equation of state either here plus, let me add the equation of state, equation of state is an equation which you can directly initialize the pressure, and you need the density as well as the energy. Since we need the density which is updating in the loop, so therefore let's do one thing. We'll initialize only the pressure here, d underscore p, and this you can also have a post loop method which runs after all the loops in a certain group. When they run, they complete, and then post loop is run for all the equations in a group. Therefore I can have here access to an updated row and the energy. I can write dp d underscore idx is equal to gamma minus 1 times d underscore rho d underscore e. Now I can have an equation of state here. Let me write EOS is equal to equation of state. My destination is air and my sources, I don't need any sources, so this can be blank as well, and this runs with the summation density. Why I can run this with summation density? Because after the loop of both the equation runs, the post loop is run. There is no post loop in the summation density, but here it gets an updated row. This is the benefit of this post loop. You can have updated values in the same group. So there is only two groups here. Now you can add a solver. So you can have this create solver. Here you can create a solver. For a solver you need a kernel. I can have Gaussian kernel. Here you have to define the dimension. Our dimension is 1, and then you have to write the integrator. Integrator is, you have to write Euler integrator, and in the Euler integrator you have to pass something like this, that what is the array name and what is the stepper for that. My array name is air and the stepper for this is Euler integrator step. If this much is done, then you can write that you can call a solver from PySPH dot SPH dot solver. From the solver dot solver import this solver. So solver is equal to solver. Inside the solver you need the dimension. My dimension is 1. The integrator is, you can check here, it should be the integrator to use. The integrator is the integrator here, and then you have to pass the kernel. Kernel is the kernel here, and then various other things that you want. For example, the final time, you already have a final time which was here. My final time was 2, so 2 seconds, and then you can also set the dt. So dt is also set, which is equal to dt, which is already defined, and then the CFL criteria, additive time step, and also various other things you can pass. Let me also write the pfrec. Pfrec is how many time step you want as an output. Let's set this to 10 for now, and then return this solver in PySPH. Now you have to write a main function. If name, then you have to create this app, the shock tube app. Then you have to say that run this, and then this will run. Let's see if this works. Let's write conda activate PySPH and then run this. There was some problem. Let's check. There is some problem here. While in the initialization there was some problems. This is row, which is an array. Here we have to convert this to a numpy array, because this was an operation for the list. For the list you cannot have this kind of operation, and for p as well you have to change this to an array. Here you can pass either an array, int, or float, or list, anything, and it will do the thing for you. There was some error again. Let's check that. You have to pass the h as well. Let me check that. Since these are globally defined, I think these are not getting passed to this particular equation. Let's do this. Let's overload this particular method. and pass this gamma is equal to 1.4 and self dot gamma is equal to gamma, and here let's write self. And while initializing this equation, we have to write in the equation of state, we have to pass this now. Gamma is equal to this gamma, which is globally defined. Let's see if in the equations we are using such other variable. Except this, there is nothing, nowhere we are using that kind of variable. Now let's try again. Clearly, if you are doing something like this, it won't take anything from the global declaration, because this goes to this particular file. I'll show you this error. Here you can see that how it changes everything to a Python, this particular file, and you can see that this has been changed to a high performance Python code. And here you can see this one is the stepper, and similarly this one is the Euler integrator. This is how kernel gradient is computed, and then momentum equation loop and energy equation loop is running here. And we can also find the equation of state somewhere declared. This one is the momentum equation, this one is the equation of state, and here you can see there is gamma here, but it is not defined elsewhere in the code. That was clearly the problem. Once this is simulated, you can see that there is a folder that has been created here, and if you check into that folder, you will see all these files that has been created. There are up to 400 iterations it ran, and after every 10 iterations it dumped the output. Since our visualization was not working, I can just use this particular operation. I can do dump xdmf and the file name, which is folder name, which is this SPH shock outputs. This one was wrong, use this. And now if I again check here, I'll also see xdmf files. No, there is no xdmf file. Looks like that this is not working, and there is no xmf file which was created. PySPH, let's try dump vtk. VTK files are created. Let's see if this one is opening. Earlier we tried, this was not working. Let's see now. Just for air, there is only one fluid, and this is just a single particle here. Maybe our simulation was entirely wrong. Maybe that is the problem. Let's try to debug this. So we can plot the particles here. Import matplotlib.pyplot as plt, and plt.plot x and y. Y's are all zeros. We can just say np zeros like x and plot them as points and then show it. This is the function which runs first. So you can see the sequence of this execution of these functions here in the main file. You can see first initialize runs, then create scheme, then all the user options are added, and then these files run. Parse command line and configure scheme, create solver, create equation, then create particles, then all these. Now let's run this again. Oh, there is only one particle in our array. Let's see what was the problem. Here we have to type xs. Yes. Now we have the entire x array. Here you can see different densities of these points. And now if we again try this dump vtk, and let's also try the other one xdmf. Now open paraview and see which one is available. We have this only. Let's try this. So there is some problem as usual, and the other one is not working. Let's also try the Docker that we had. Let me first activate Docker. Once this is activated, I can check all the images that I have. Let's try this one, Docker. Let's add this particular folder, write this folder name, shock output. if you go to this SPH, we get the file. No, no, this is still not shared. Okay, here we have all the files. Now let's try this SPH. We have SPH dump xdmf and the PySPH folder. This worked. Now we can exit, and now let's check if we have the output here. Clearly it created this xdmf file. Now let's try to open this in ParaView. This one was working, so you can see that it opened this particular file, which is just, as you already know, that this is just the single 1D line, and using this alphabetical plot over line you can plot various values. Right now it's not plotting anything because I think it did not output everything. One other thing that we can always do, so since this is a 1D simulation, nothing much was observed here. And also remember that this Docker container was from the latest version. This PySPH is something that I installed way back. For the latest one, the XDMF dump is working. Now you can always do a post processing. Here you can have a post processing. You can copy from the existing post processings that are there in PySPH. You can go here and go to PySPH examples and look at any of the examples. Let me look at just the cavity. So in the cavity example, go to this, how it is loading all the files. This is the post process. From this you can get all the files. Let me copy this thing. This is a bare minimum that you have to do. This import is not required because our matplotlib is working, I know. And then this is the important thing, that you have to get the info, and then you have to read the files as well. Let me load some files. In order to read the files, this is the load method that you have to use, and these are how you can get the files. Let me copy these two as well. And since it's a 1D, you don't have to do any interpolation, so we are not going to do interpolation, but you can also do interpolation along any line or any surface you want, and just define the surface points and you can perform the interpolation. Here, from all the outputs, just take the last output, or you can just take all the output files and then plot for all the files. Let me do that. For file data in fname, let's write this as fnames. It will give us all the names. Here you can actually load it. Let me just write fname here and write data is equal to load fname. And inside data, the structure is as follows. First you have to access the array. Array is data, all the arrays, and then the array name. In order to access the x values, you can write x is equal to air dot x. Similarly, pressure is air dot p, and velocity is air dot u, and rho is air dot rho. We have not saved energy, so I'll save it. First I'll show you that if you just want to run these, I'll print for now x, p, u and rho. So you can just perform the post processing by running this python, the file name python sph shock.py, and then post process the file name as well, the folder name. You have to pass the folder name and then it will perform the post processing for you. Here from the matplotlib I can create axes and figures. I need subplots and I need 2 rows and 2 columns, and for these you can share x and y, but that we can skip for now. And now axis list, you can write as, you can ravel it so that you can get it as a list. Now axis list 0, you want to plot here x and p and label it as pressure. Similarly, others, in this you want u and write velocity, and then rho, you can write density, and the last one is for energy, but I'll just do pressure again. Here you have to write 1, 2 and 3, and for now let's just do pause 0.1, and then it will plot for each and every result. Let's see what is the output. Figure and axis. Figures are here, then axis. We have to clear this as well. Let's clear this. Let's make this as 1 second, and for axis in syslist, let's write clear axis. Clearly this looks weird. Let's see the problem. From the end as well, we are getting some values which we don't want. For that, we can do one thing. We can add periodicity. In order to add periodicity, you can go to any periodic example. Let me go to Taylor-Green problem, and from here, in order to have periodicity, you have to add this create domain. Just this function, if you add, then you will get the periodicity feature. For this, I have to add the domain manager as well. Add the periodicity, and this one is, we know this is till length, which is given, and along y there is no periodicity. We don't want anything, so periodic in x only. And one more thing that you can do is, you say that an NPH should be updated after this, because once you compute the density at the ends, you want it to be updated in the periodic particles as well. With this, let's try again. Now we'll run the entire thing. Let's plot the particles only. Set title so that we know that which plot is which. Pressure, velocity, density, and pressure again. This is velocity, this is density, and this one is pressure again. Let's put energy here. We'll change it later. Actually, let's do it now. In order to output more arrays, you can just do something like this. You can say that in the particles, you want to set, you can add output arrays, and here I'll add E as well. Once you do this as a property, then you can have E here as well. Right now, if I run just the post processing, it plots everything to 0 when these things are not present and you call this. That's why you are getting all zeros here. Energy is not provided, and this one you can see here as well. Let's fix that. This should be 1, this should be 2, and this should be 3. And rho, pressure, velocity, let's output everything that we need. Pressure, velocity, and rho, and finally x. We want x as well, even if it is present. Let's write that so that there is no problem. Again, let's run this, and now if we post process this, then we are getting all the values. Here in case of velocity, we get this in the negative side first. Now let's see the results of the previous version. This was for velocity and then density, and this one was for energy. Clearly it was like this, not that stable. Similarly here also we are getting that, but the velocity is in the negative side. The initial velocity that you are getting is in the negative side. And again there is some problem here, even though we have used periodicity. Let me just make sure that it is right. Starting from this that, and periodic in X is true. Okay, periodicity in X true will not work because at the end we have different property values as well. Clearly this is not going to work, and we are still going to get some error from the other side. Again, the velocity on the negative side, and also we are getting this shock on the other side. It goes towards the negative direction. Probably these values are not set right. So that you can debug on your own, but you can see that the same kind of physics we have simulated using the PySPH framework, and we were able to do this in a much more systematic manner. These all the equation can be reused if you have some other simulation which requires momentum equation or energy equation or equation of state. You can reuse them. You can edit the values easily. Everything is available. You can call this particular class in some other Python library and just edit few parts to simulate this again on some other set of properties. So this is how PySPH framework is very helpful, and in the next lecture we'll simulate a little bit complex problem where boundary conditions will also be involved. If you like the content of our channel, then please like, share and subscribe. Thank you.